Hi, and welcome back to the UNR R Bootcamp. We are in Bootcamp 1, Module 3, Plotting and Basic Statistics. And we just went through basic graphical functions, and now we're going to go through some stats. Now, here, let's get to the stats. You can just go to the left-hand menu and find the basic statistics. That's where we're starting. Now, this boot camp is an intro to R and programming in R. It's not an intro to statistics, but since R was originally developed as a statistical computing language, and that's its primary use, it would be remiss to not go over at least a little bit of basic stats in R. As you probably know, R is developed from a statistical computing software called S and S+, and R is the free open source version that descended from those statistical software. So let's go back to our studio, and we're going to continue working through the script for this module and find the place in the script where it says statistics. That's where we're starting. And as I should have done, I should have let's go back to the website for 1 second. I just want to get the data set that we're going to be using. It's a data set on sculpin, which is a kind of fish. And we have basically female, we have a bunch of sculpins. Each row represents a different individual, and we have two measurements on each fish, or two columns in the data set. One is the weight of each female, and one is the number of eggs that she produces. So let's get this data set. Just save this link right to your working directory, and it should be called sculpineggs.csv, and just save it right there. And now we can go back to our studio and we can load it in. So let's load that data file in using the read.csv, and we can get a summary. This is a very simple data set. It just has two columns, again, female weight and the number of eggs. Each row represents a different fish. All right. Before we do any stats, we probably want to look over a new data set and do some summary stats. So let's just do that. We can review some of the summary statistics that we have gone over already. We have the mean. We haven't seen the median, but there's another function called median, which computes, obviously, the 50% quantile. And we can get the minimum value for the column num eggs. So this is just a vector, and the min function just gives us the minimum value in the vector. Same with the max function, gives us the maximum. And if we want to do both in one fell swoop, we can use the range function, which gives us both the minimum and the maximum at the same time. There we go. The quantile function is a useful and flexible way to compute any quantile we want to compute. So if we want to compute the median but use the quantile function, we can compute the 50% quantile. That is the value where 50% of the data essentially are below that value and 50% are above that value. So it's kind of the middle value, and compute the 50% quantile for the number of eggs, and that's 87 for this fish. And we can also compute other quantiles like the 25% and 75% quantile. 25% quantile is just 25% of the data are below that value, 75% above that value, and the reverse for the 75% quantile. Those are special quantiles. Those are called quartiles. And so we can compute those quartiles. We can compute the variance, and the variability in the number of eggs among fish. A good summary statistic, but an even more common one is the standard deviation, which is the square root of the variance. And of course, if we wanted to compute the variance, we could use the standard deviation and square it. So just a review of different things we can do. There's another way to do the standard deviation. All right. We can, with one function call, or one command, we can compute the means for every column in a data frame using the call means function, a convenience function that R gives you. Let's do that and see that here we have the mean for both columns at the same time. There's other ways to do that as well. So again, we can't get stuck because there's a million ways to do things. We could use the apply function, which is a very flexible way to compute summary statistics across rows or across columns of a data frame or a matrix. So the way apply works is we give it a data frame or matrix or array, and we specify the dimension across which we want to summarize or compute summary statistics. If we said 1, that would mean we want summaries across rows. If we said 2, we want summaries across columns, which is just what the col_means function does. So let's do that. And we have to, of course, specify what function we want to summarize across columns. And so we want to use the mean function to summarize across columns for this data frame, sculpin.df. So let's do that. We get the exact same result as the col_means gave us, and we could compute other statistics using the same apply function. This is what makes apply functions so incredibly flexible. We could even specify our own function. We don't have to resort to functions that base R provides or other packages provide. We can use other functions to summarize across columns in this case. So let's use the median. We can summarize the median value, and if we wanted to, we could take the mean across rows just by changing that 2 to a 1, which means I want to summarize across rows, and that gives us the row means for every row in our data set. How many rows are in our data set? We have 11, and that should be the length of this vector here. All right, and of course, we already have seen the summary function when applied, when a data frame is given as an argument between these two parentheses to the summary function, it summarizes every column in the data set very conveniently and gives us even a summary of how many NAs are in the data set, the median and the mean, and the quartiles, and the minimum and the maximum. So kind of does everything for us, but kind of useful to see how it's done piecemeal as well. All right. Just a quick reminder that if we did have NAs, notice that this data set doesn't have any NAs, so that is no missing data. Easier to work with that way. But if we did have NAs and we tried to do some summary statistics, like the mean, we'd have to use this na.rm equals true argument. That tells us that we want to remove all the NAs before computing the mean. So in this case, we could go back to our missing data data frame and just read that in. And if we compute the mean, it doesn't actually give us anything because it doesn't know what the mean is because it's missing at least one value. And so for it to give you a value, we have to use that argument here. All right. Before we do stats, we want to do some plotting. We've been through plotting, so we can do a histogram of the different columns. We can do a histogram of the number of eggs in this case, or we could do a histogram of the female weight if we wanted. So see what that looks like and just get a histogram that way. So really easy to do these kind of like basic visualizations. Here we can do a scatter plot where we are looking for a relationship between female weight and number of eggs. You probably want to think a little bit about which variable you want on your x-axis and which on your y-axis. Usually the dependent variable is on the y-axis. The independent or predictor variable is on the x-axis. We can kind of think of this as we want to model the number of eggs as a function of female weight. So female weight would be on the x-axis and the number of eggs would be on the y-axis. So we can specify that directly in the plot function, saying the y-axis is the number of eggs, the x-axis is the female weight. And let's do that. Of course, we don't have great labels and everything, but we've been through how to do that already. What we do see here is that there's a relationship. There's at least what appears to be a fairly strong statistical relationship between number of eggs and female weight, but this is just a visual impression. we need to run some tests to see if that relationship holds up and if it is stronger than you would expect to see with just random sampling error. So that's where we do statistics. And this is where we get into some statistical modeling in R, which is one of the things that R does so well, and what so many statisticians and scientists across the world have expanded the functionality of R to run all sorts of sophisticated, state-of-the-art models. And we're going to just barely scratch the surface in this video, but this is where you really have to go off on your own and learn the types of techniques that are going to benefit you. This is just a very bare bones introduction. Here we're going to use the LM function, which stands for linear models. It's basically a function for ordinary linear regression. And so we've seen this syntax before. This tilde can be read as is a function of. So we're going to model number of eggs as a function of female weight. All right. So hopefully that makes sense. That type of syntax is a part of almost all function call or statistical modeling calls in R. So you'll see that a lot, and we've already seen it. We can use it in making calls to the plot function as well. So we give it this formula. This is called a formula, and we give it data. And the elements in the formula, of course, have to be the column names in our data. So we're going to model the column named num eggs as a function of the column labeled female weight, and we give it the data. Now we don't have to give it the data. We could use the $ notation here. So we could do it like that, and it would give us the same result. But I recommend using the data argument. It's going to make your life easier, and it's going to make the summaries from the model more readable. So let's run this model. Note, R doesn't return anything. It just is waiting for another command, but we do have a model up here, and that M1 that we just put in our global environment on the basis of this last command. We assigned this object M1. That object is a model object, so it stores the results of a fitted model that R has fitted using the algorithm in the LM function for linear regression, essentially. So now we have this model object. We can look at the model object. R's default, when you just type in the name of an object, is to print out what's in it. And it gives us a really bare bones summary of the statistical model that we just fitted. It gives us an intercept and a slope. It tells us the call that was used to make the linear regression model, but it just gives us an intercept and a slope. It doesn't give us any confidence intervals around those parameters, and it doesn't give us any R² values. So we might want to get a more detailed summary, and to do that, interestingly, we use a function that we've seen before. It's called the summary function. What's interesting here is that when we give the summary function a data frame, it knows to summarize the columns of that data frame. When we give the summary function a model object, it knows that we want a more detailed summary of the model, including confidence intervals and R². So let's run that. So the summary function is quite flexible depending on the type of object that you feed it. And again, it gives you the call. This time it gives us a summary of the residuals. It also gives us some coefficient estimates, which are the same coefficient estimates we saw up here, but it gives us standard error on those coefficient estimates, which is really important for determining if those estimates, if those coefficients are more extreme than you'd expect based on random chance. Gives us a basically sense of the sampling error in that coefficient estimate. Gives you a t-statistic for the intercept and all of the regression coefficients, which again is used for testing significance, doing hypothesis testing, and it gives you a p-value, which in this case says that there's a very, very low chance of this regression parameter, this coefficient, being produced by random chance. If values as extreme as 1.87, that coefficient value, being produced just by random sampling variability. So very low probability of that. That's what the p-value is saying, and it gives you some asterisks to say this is a very significant statistical result. All right. So and it gives you other summaries that we might be interested in. It gives us an adjusted R-squared and an R-squared, which tells us that the female weight is explaining a lot of the variation that we observe among individuals in the number of eggs produced. So the female weight can be potentially quite explanatory for predicting the number of eggs, and it gives you an overall model p-value and an F statistic. So much more detailed summary of your model. The summary function is going to produce different results for different models. It depends on what type of object you're giving it. For a linear modeling object coming from the LM function, this is the summary it gives you. All right. Not going to go too much more detail there. We can pull important summary statistics out from this summary object. So note that we're using the $ operator to extract elements from a list. That's just that's what the $ operator does. In a data frame, we use it to extract a column of the data frame because each column represents an element of a list, right? So we went through that in the first module. But if we want to, we could save the results from the summary function applied to a model. And so now we have this object A, which is what is returned from the summary function for a linear model object. And then we could, in which it happens to be a list, by the way. And so then we can extract an element, any element of a list, using the $ operator, and we can extract the R-squared from that object. If you don't know what that summary object looks like, remember the str function. That's going to give us a summary of what's in that list object. So we can see that there's a lot in there, but our eye might be drawn to some keywords here. Like we see R-squared here. That tells us, okay, that's the R-squared. We can grab that R-squared just by using the $ operator and grabbing that list element. We can grab the adjusted R-squared just the same way. And RStudio makes it really easy because when you hit that $, you can just scroll down to whatever statistic you want, Control Enter, and get that statistic. So it's really useful to know how to explore different objects so you can extract the information you'd like to extract and use those objects the way you'd like to use them. So that str function comes in really, really handy. All right. We can use this conf_int function, give it the model that we just fitted, this M1 model, and it will automatically give us confidence intervals on our regression parameters, including the intercept and the slope of this relationship between female weight and the number of eggs produced. So that can be really useful. Confidence intervals are really important to present because it gives us an idea of how much sampling uncertainty there is around these. And because the confidence interval on the regression parameter here does not intersect with 0, it means that this is a strong relationship. Again, very little chance that this could be produced just by random sampling error. We can use the AIC function, and most of you have probably heard of AIC. It's Akaiki's information criterion, and it's really useful for performing model selection. When you have a bunch of different models, maybe with different covariates, and you're trying to figure out which is the best model, AIC helps us to do multi-model inference. When you have a bunch of plausible models, which one is the best or which set of models perform well, and are plausibly the best model, use AIC. It's a good, commonly used way to do model selection. All right, so let's plot our results again. And now what we're going to do is plot a regression line on top of this scatter plot, just to visualize the relationship between the female weight and the number of eggs produced. The AB line function is a convenience function for drawing lines on top of existing plots. When you give the AB line function a model object, it will plot the regression line. So that's a nice, easy way to plot a regression line on top of an existing plot. And if we wanted to change the color or the line width, we can easily do that. So we can make a blue line and make it really thick if we wanted to. So all the graphical parameters that we've gone through already apply here. Another really useful function for working with model objects is the predict function, because this is going to give us an ability to predict to observations we may not have made yet, but we might know what the covariate value is that we want to predict for. So imagine we want to predict what the number of eggs produced would be if we had a female that weighed 50, whatever these units are. So we could make predictions for any values of our covariate. We can make predictions for our response variable, what we predict the number of eggs should be. So the way to do that is we first create a data frame that represents all the observations we'd like to make predictions for. This data frame has to contain all the different covariates that are included in our model. In this case, we just have one covariate, and that is the female weight. And it has to be that the covariate name has to match the name in the model object. So if we look at M1, we can see that it has one covariate, and its named is FEMWT, all caps. R is case sensitive, so you have to pay attention to that. So now we have female weight, all caps, and then we provide whatever female weights we'd like to make predictions for. It doesn't have to be just one. We could potentially do several. So maybe I want to make a prediction at 30, and I want to make a prediction at 60. So to a value that we have no way of knowing. Now 30 is also, we don't have any observation at 30. There's no point in the scatter plot right here. So we're also kind of, this is called interpolating. We're interpolating because we have observations both below and above it, but we don't have an observation right at 30. So we're making a prediction here that's called interpolating. For 60, we don't have any observations greater than 60. In fact, 60 is well above the largest observation we have for female. So that's called extrapolating. All right. So we're going to both interpolate here and we're going to extrapolate. Just take a look at the data frame we just created. It's going to have one column and two observations, one for 30 and one for 60. And that's all we need to make predictions. So we're going to end up making two predictions for the number of eggs because this new data object has two rows. And so let's make some predictions. And we've now made two predictions. So it says that at 30 grams, let's say, we should expect 75.9 approximately eggs produced, and at 60 grams, we should expect 132 eggs produced. All right. We can also use the predict function to provide confidence limits on our predictions, which is really useful. At least if you give it a linear model object fitted by LM, you can tell the predict function that you want a confidence interval around that prediction, or that you want a prediction interval around that prediction. The confidence interval gives us the sampling error around the mean expected value, and the prediction interval gives you the error around the expected observation itself, not the mean if you took multiple readings, but just if you took one, or if you took a bunch, like how variable, how much variation, how much noise would there be. again, don't worry. This isn't a stats class. Don't worry if you didn't get that. But you can produce both confidence intervals and prediction intervals for every prediction that you make from this function, predict. We're going to come back to predict in just a moment, but let's do a quick model selection. We talked about using Akaiki's information criteria and AIC to do model selection. Let's just run through a really quick model selection exercise. This will give us some more experience working with the formula interface, trying a bunch of different models, and then comparing them using AIC to see which one is the best model. So let's first explore an aspect. Before we do that, you see that the model selection example is actually right here. There's actually one thing before that, is just to look at this syntax for the model specification, and specifically the formula specification. That is this is called a formula with that tilde. So number of eggs is a function of female weight, caret 2 here, and here's another formula interface. Number of eggs is a function of female weight, caret 2, but now enclosed in this I function within the formula specification. So what's going on here? Well, the idea is, and this is something that is kind of useful to go over because you might see this and it's not immediately apparent what it's doing. So let's imagine we want to model number of eggs as a function of female weight squared. All right. So if we use that, let's just go to the Sculpin DF. I'll just type it up here. It's easier for you to see up here. So Sculpin DF, we're going to pull out the female weight. And if we use this caret 2, we're going to square the weight. So we're going to take each observation and we're going to square each observation, and it'll look like this. So this is the square of each female weight as measured. So what we're going to try to do is model number of eggs as a function of the square, female eggs squared, so that you'd think that because the caret 2 squares any object, a vector or matrix or whatever, that would be the same within this formula interface. So you might think this is the way to specify, I want to model a quadratic relationship between female weight and number of eggs. So let's do it, and we can summarize this model, and let's compare it to the original model that we ran. I'll just type it out here. So what are the coefficient estimates? For the original model, 19.7, 1.87, 19.7, 1.87. It's the same. We didn't actually do anything different. This is exactly the same model as we fitted before, because within the context of an R formula, in a model formula, this caret symbol means something totally different. It doesn't actually mean square it. It actually means something about interactions. Don't worry about this, but if you had another covariate in here, you could model interactions. So, say there's another covariate, and you did something like this. Well, it wouldn't even matter here. Say there's another covariate, 3. What this is going to do is it's going to model all the additive effects of these 3 covariates, and only the 2-way interactions between these covariates. It's not going to do the 3-way interaction. Again, if you don't understand that, it's not important. This isn't about, we're not going to get into that kind of detail here, but just know that it has a different meaning, that this caret 2 has a totally different meaning than it did when we used it to square a vector. All right. So when you see this I function within a formula, what it's saying is you can interpret it as is. So now I'm using the I to say I want R to interpret whatever's in these parentheses as it would outside of a formula interface, just in base R. I want to interpret it like this rather than as if it were part of a formula. So that is, I want to square it. I want to square that covariate. I don't want you to think of this as the specialized meaning that it has within a formula. I want you to think of it as R does in every other context. So think of this as is. So this is a way we can actually model the quadratic relationship, all right? Because this did nothing compared to the base model. This will model the square of female weight, or number of eggs as a function of the square of female weight. And we'll see that in fact, the coefficient values are different now. So that's something you'll probably see as you go looking at other people's code and running through tutorials and stuff. And it's kind of a useful thing to know, because it may not be immediately apparent what's going on. So that's what the I is for. All right, now we can work through a basic model selection exercise. So we're going to run a few different models. We're going to run models where we're always trying to model the number of eggs, but we're modeling the female weight with different types of transformations. For instance, we will model one with the square root. So we're going to use the square root of female weight as our covariate. We can use female weight untransformed as a covariate. And we're going to use a third model that has no effect of female weight at all. That is the null model, where there's no effect at all. Let's run those models. We have M1. We've already run M1, but we'll run it again. Now we have M2, which is our null model, and M3, which models number of eggs as a function of the square root of female weight. One qualitative way to look at the degree of fit for each of these models is just to plot out the scatter plot and just plot out the relationship. So here we have M1, which is the line of the regression line for the basic linear regression model. We have M2, which is the null model. We'll plot that in red. Obviously doesn't look as good. We can tell immediately that that one's not so great. Can we do that with M3? If we try model 3, remember what's happening here is you have the female weight is taking the square root. So the covariate is going to be nonlinear on the scale of female weight. So let's see what would happen if we tried to put a green line here. It doesn't look great. And the reason is that the AB line function isn't very powerful, and it's not able to do this nonlinear relationship. So we'd have to come up with another way to do this. I'll just comment that out because that obviously doesn't work. It didn't do anything. So here's another flexible method for drawing that line that we couldn't draw using the AB line function. In R, we always have ways around problems. So this is a problem, but it's a solvable problem. We can get around it by using the predict function. So first we're going to make a data frame for prediction. And again, since female weight's the only thing we want to make predictions with, it's the only column in this data frame. But instead of just giving it a couple things we want to make predictions for, like we did before, we're going to give it a whole sequence of values that we'd like to make predictions for. These values represent female weights for unobserved individuals, and we're going to vary this from 10 to 45, and we're going to do it in a really fine-grained way. Every element separated by only 0.1, so we're going to make a long sequence from 10 to 45, and this will make our line nice and smooth because we're going to make predictions for each of these elements. Predictions, because each of these elements represents a female weight, we can predict on the basis of our models the number of eggs, and we're going to do that in the next line. So we're going to use the predict function, give it the model, give it the new data that we just created, that data frame, and that gives us predictions for every one of those observations across this spectrum of female weights. And then we can use the points or the lines function to generate or to add this this curvilinear line or regression relationship into our plot. So a points function is a convenience function for adding points or lines into a plot. We're specifying that we want to add a line because we say type equals L. So let's run that. You can see that it does add this green line. It may be a little bit difficult to see. We might want to zoom in, and you can see that there's this curvy green line that almost looks like it's right on top of the linear line, but it's not quite. And so now we do have that third model represented in this figure, which is kind of cool. So we use the predict function. It's a very flexible way. You can do that with all sorts of nonlinear regression models. All right. Which model is best? Just by looking at this figure, we can see that obviously the null model is not fitting very well, probably is not the best model, but there's very little difference between model 1, which is the line, and model 3, which is the nonlinear relationship. And let's look at the AIC values. Now we're looking for the smallest AIC value. The lowest AIC value is the one that represents the best model. So AIC for model 1 is 86. Now, just interpreting the absolute value of AIC isn't very useful, but looking at it relative to other models, then you start to get some information. So AIC for model 2 is 100. That's a lot greater than 86. We interpret differences of about 2 as being meaningfully different. And so these are very meaningfully different values. The null model is not good, as we can see just based on looking at the figure. What about model 3? 86.87, just a little bit higher than the linear model. So they're both plausible. They're within 2 of each other. They're both plausible. But since the linear model is a bit simpler, we'd probably go with the linear model as the best model. All right. We can compare the models using R² if we want. We have the R² for model 1, model 2, and model 3. Model 2 has an R² of 0 because clearly female weight explains 0% of the variance in the null model because the line is flat across that spectrum. But both model 1 and 3 explain a good amount of variance. Model 1 explains a little bit more than model 3, which is along with what we just showed, that model 1 is in fact a little bit better than model 2 according to AIC as well. Finally, before we end this module and you go on to your challenge problems, let's draw the confidence interval on top of this this relationship. And we'll do it with model 3 just to show how to do it with a nonlinear relationship, because that means if you can do it with a nonlinear, you can do it with almost anything. So we're going to again use the predict function to go through a very flexible way of adding confidence intervals to a regression relationship in R. All right, let's start with a blank scatter plot. We're going to try to add a regression relationship and confidence intervals on top of this plot. So the first thing to do is and we already have this female weight .pred object that we created up here, and it looks like this. It's just a data frame going across a full spectrum of female weights that we're interested in, from the low to the high end of this plot. And we're going to be able to use that to make predictions. So for every one of these rows, we're going to predict the number of eggs corresponding to this female weight, which is the name of the column in the new data argument. So we're going to give that as the new data argument. We're going to feed it model 3. So we're going to make predictions from model 3 for all these different potential values of female weight. And we're going to include a prediction interval on top of each prediction. So let's run that line. And you'll see there'll be 3 columns in this. The first column represents the fitted value, or the mean value. The second represents the lower bound of our prediction interval. And the third column represents the upper bound of our prediction interval. If we want to add the fitted, and each of these columns actually has names, so we can use those names to call the columns in this object. And we see that we have the named columns. So we have column named fit. That's the mean for the expected value for each value of female weight. Then we have the lower bound and the upper bound of the prediction interval for each prediction of number of eggs. All right, so we can add the fitted relationship. You see that's a little curve to that because we're using model 3, and we're specifying we want a green line. We want it to be a line and not points, and we're specifying that we want the line a little wider than the default. We can do the same thing. So we'll use the points function to add the lower bound and the upper bound. This time, let's see what it looks like. There's the lower bound. We're saying that we want line type here. Line type equals 2, which means that we want a dashed line. So that's why it's giving us a dashed line here, and we'll do the upper bound just the same way. So again, a really flexible way to add not just regression lines, but also confidence bounds on your regression line. And that's a great summary of any statistical model in R, and it's a great way to communicate the results to others. That's basically the end of the statistics portion. This is obviously very, very quick intro to stats in R. There are lots of other resources online if you want to go further with stats in R. And with that, I would encourage you to work through the challenge problems, and please let me know if you run into any problem areas or issues that you'd like to discuss. All right, I'll see you in the next module.